Well, good morning, everyone. It's a great pleasure to be back at the Fields Institute. I was last here in 2019, and then we had this gap. But it's really great to be back here at such a great meeting, which is full of such great ideas. So my talk is actually quite linked up with the last one, and also addresses the point that Yanis Kevrakidis made a couple of days ago, which is you gain a lot when you look at the where you look at numerical analysis informing deep learning, and also deep learning informing numerical analysis, where you look at the interplay between the two. So this is a sort of meeting on dynamics and deep learning. So I'm going to look at quite a general dynamical system, namely, is it that one? Yeah, there we go. Suppose we want to solve some sort of PDE, time evolving, and quite a significant spatial dependence. If we were going to do this in a traditional numerical analysis way, what we would do is we construct some mesh. This is a mesh constructed adaptively to fit a non-convex domain. And then you discretize your PDE on that mesh and solve the resulting discrete system of equations. So that's traditional numerical analysis. One of the problems with that is that the accuracy and efficiency of that method depends hugely on the mesh that you construct. And there's a vast amount of software. People spend their lives, myself included, trying to work out where to put the meshes, especially for problems which are non-convex or time evolving and all that sort of stuff. So that's classic numerical analysis for solving a dynamic PDE evolving in space. So where are we now? Well, the great new idea, in a sense, is the idea of using deep learning to try to avoid some of these issues. And some years ago, we had the first few papers on PINNs, that's physics-informed neural networks, which try to solve PDEs or ODEs in a mesh-free way. So the idea of a PINN is that rather than having a mesh and approximating the solution over a mesh, you have a functional approximation of the solution, which comes from your neural network architecture. That functional approximation is differentiable, and then you can use that to represent the residual of your PDE, and then you solve using standard learning methods. So that's the PINN, and PINNs have achieved great results on some problems and have achieved rubbish results on others, and we're still not very sure when they're going to work and when they're not going to work, and that's partly what I'm going to talk about today. So that's a PINN. Very exciting, lots to find out about them. The idea of then using a PINN, as I say, is to use the functional approximation of the function you want to solve within your deep neural net. Now, there's a very interesting point which we can make immediately, which is, let's suppose that we use, say, a shallow neural net like this to represent a function, and we use a ReLU function, which is linear on one side and 0 on the other. So we get this here. Then it's very easy to show that the ReLU approximation, whether you use deep or shallow, is actually a piecewise linear approximation of the underlying function. So classic numerical analysis, finite element methods rely on piecewise linear approximations. So there's actually a very immediate link between ReLU and classical numerical analysis. But there's one intriguing and important difference. In a ReLU approximation, you have what we call the knots. These are the points where the kind of discontinuity of the derivative of the ReLU activates, and those are given by this one divided by this one, and these are unknowns. So in a neural net ReLU approximation for a function, this is equivalent to what's called a free knot piecewise linear approximation of a function, which is a much more nonlinear and much more interesting object than classical finite element, where the knots are defined in advance. So that's a very interesting link and allows us to draw an analogy between finite element and PINNs, which we're going to kind of have a look at and see how everything works. Okay, so let's talk about how a traditional PINN works. So a traditional PINN assumes that our functional representation, which I will always denote as capital U, has strong regularity. Typically, we need to be able to differentiate it enough times to exactly substitute it into our differential equation. We then differentiate that using back propagation and all the kind of tools we have available in the neural net. We then evaluate the residual by substituting that into the PDE at a set of collocation points. Okay, collocation points. So these are the points where you evaluate the residual, and these can either be uniform, so we have some sort of uniform mesh, or random, which is kind of more in the kind of traditions, as it were, of deep learning. And once you evaluate that, you can then use the kind of neural net to minimize the loss function using Adam or whatever you want to use. And at the end of the day, out pops your solution of the differential equation. So that's the action of a traditional PINN. So they're claimed to be mesh-free methods. They're not. They have a mesh-free representation of the solution, but actually these collocation points here turn out to be rather important when it comes to the ultimate accuracy of the PINN. And we'll have a look at those both in 1 dimension and 2 dimensions in this talk. So that's the operation of a traditional PINN. It's pretty similar to the traditional numerical analysis method of collocation, except you can train collocation methods in a somewhat different way, but otherwise it has some strong similarities to that. So let's have a look at a quick example of this working. So here's a simple 2-point boundary value problem, classic nonlinear second order differential equation with boundary conditions at 0 and 1. And then we represent that using our neural net to form a residual. Here we have it. And then our PINN is obtained by minimizing a combination of that residual evaluated at these famous collocation points together with a boundary term which you can weight in various ways. I mean, there are various ways of weighting the boundary and so on, depending on the problem. And then you can hit that with whatever you want. You can hit it with, say, Adam or whatever. And as you go through, we find that the loss function nicely reduces, and rather nicely, the error on that reduces as well. So the PINN is doing quite a nice job here. Here we have a very, very simple problem, one carefully constructed so we know the answer. Hopefully you can work out the answer to that in your heads, the answer being that, which isn't very difficult. And the PINN has nicely represented the solution. And in fact, we get a very good rate. If you increase the number of nodes in your PINN, then the convergence on that goes like 1/n squared, which is about optimal for that sort of thing. Okay, so that's a PINN working nicely, but they don't always work nicely. As I say, one of the big assumptions that you make in a PINN is that your solution has twice differentiable regularity. For many, many problems, you don't have that. And so more recently, what's become kind of quite popular are what are called variational PINNs. And in a variational PINN, you assume that the solution has a weaker regularity, e.g. H1 being Sobolev space, and you differentiate U as many times as you can consistent with its regularity, and then approximate the PDE in various sort of weak forms, and then you evaluate the weak form using quadrature or whatever. Again, these are not quite mesh-free methods, because although you represent your solution in a mesh-free way, you still need to choose where your quadrature points or collocation points are. That turns out again to be important. And then you train the neural net to minimize this. And people like Wayne Anti and so on have come across, have used these sort of things. So that's a variational PINN. And we'll come back to those later on in the talk. So here are some very good questions. I mean, these are questions for the workshop. These are questions about PINNs, about solving dynamical systems using deep learning. Firstly, when do PINNs work? When don't they work? And why? Okay, answers on a postcard, please. Secondly, does the performance of these things depend upon where we do our collocation and quadrature? The answer is yes. And can we learn, in a sense, where to put these points as part of the overall solution problem? And then this is the kind of what I call the Kevrikides question. Are PINNs working because they're basically numerical methods in disguise that we know and love anyway? The answer is sort of. Okay, so these are the sort of things I want to look at. And the first one actually relates perfectly well, very, very well indeed, to the previous talk. So thank you for that. And the question we want to ask is, a PINN is trying to solve a differential equation. Now, as I said, if a classic method, you use finite element method, and finite element methods are fundamentally approximation methods. You're trying to approximate something over some finite dimensional space. So we can't really use a PINN or understand how a PINN works unless we can understand how we can approximate functions using a deep neural architecture. Okay, good news and bad news. Before I get on to my next slide. The good news is we know that deep learning can approximate things perfectly. We've got the universal approximation theorem. That's the good news. The bad news is that that's a non-constructive theorem, and it doesn't actually tell us very well how to do it. And I'll talk about that in a second. Okay, so here's the question we want to ask before we can even use a PINN. Let's suppose we have some simple architecture. Feed forward will do for what we want to do. And we have some function f, some function u we want to approximate, and f is the approximation doing that. How can we approximate? Well, let's suppose we do this naively. A very straightforward loss function might be, let's look at the mean square error of the thing evaluated at our series of quadrature points, where, as I said, f is with ReLU a piecewise linear approximation with 3 knot points. Okay, totally obvious that we should do that. A perfectly natural loss function. Okay, and as I say, we know out there is a perfectly good approximation. The universal approximation theorem tells us there is something sitting around if only we can find it. What's the problem? This is a terribly non-convex problem because it's so nonlinear, and you can't find the brute. So you can go off and try to do your best, and this, this is sine. This is the function which the PINN quite happily computed, but if you try to find it in an approximation theory method, it's awful. Your loss function kind of minimizes, but that's the approximation it's come up with. It's absolutely dreadful. And the reason it's absolutely dreadful is it's got itself into a local minimum and won't get out of it. Let's have a look at another function, x to the 2/3, which we'll come up against later. This has a function which has actually got a derivative singularity at the origin. And this is even worse. I mean, the loss function's hardly gone down. It's absolutely dreadful. So although we know we can approximate that, it's continuous. I can certainly write down a very good piecewise linear approximation of that. The classic loss function isn't actually able to find it. Okay, so what do? Well, we know there's a solution out there. The problem is not in the deep learning, because the deep learning could find it if it was treated nicely. The problem is basically in the loss function. And if you can change the loss function, here's a really nice one. This is a function, I know it looks a bit weird. You've got all this nonsense here. But this is a function which you can show using a traditional numerical analysis ideas has the property that it should find the right kind of knot points to find our solution. It's basically based, instead of on the L2 error, on the error that you expect to get using a piecewise linear interpolant, which is what's going on in a PINN anyway. So we replace our loss function with this, which is familiar to anyone that works in adaptive meshing. And this is sort of mimicking the action of the PINN. The PINN is minimizing residual error, and now we're just trying to do straightforward approximation, but using instead a loss function which mimics the residual error. It's using the interpolation error, which is actually a much easier thing to estimate in advance. Okay, so you stuff that into the whole thing, and what happens? It works. And what you find is if you take x to the 2/3, which is a horrible function because it's got a derivative singularity, even though it's continuous. And you do your classic learning, it suddenly falls off the end of the cliff and you get a very significant reduction in loss. And if you do a calculation of the error as a function of n, then using this method, you actually get a really good error. You get a very good representation of the function. And in the Nibel norm, that's what it looks like. In fact, you get a better representation of the error than you would if you had a uniform mesh. So this is why I think PINNs might be working well. It's because the loss functions that they're essentially using to approximate functions are not the loss function you come up with if you just naively thought about it. They're actually one relatively well tuned to approximate that function. So I think that's what's going on. There's no theorem yet. That's on its way, I hope. But that's what I think is going on. And just to say, one way to kind of see how good this is that you can prove that the optimal knots must satisfy what's called an equidistribution condition, and your closeness to that is a good measure of how well you're doing. And the PINN, which is the deep neural net here, actually outperforms any other method that I know to do finding the best function approximation. And I've been in the business long enough to know what these other methods are, and I was very impressed that it did so well. And as I say, that might help explain why PINNs work well in certain cases. So that's kind of the kind of approximation theory point of view. And you can actually sort of use this a bit more. Let's suppose we want to use a PINN to solve a dynamical system. We can say immediately, well, we know from this kind of earlier thing where we might want to put our collocation points. They're linked up with this interpolation error. And that gives us an idea that we could kind of speed up the whole PINN process. So rather than trying to train on random points or uniform points, you might actually want to train on points where the training would be most effective. That's these kind of points. One idea is to try to train the two together. I say that's the semi-Lagrangian approach. In progress, but semi-promising. Semi-promising means it doesn't always train, and we're not sure why. But what we call the rezoning method works really rather well, which is you do a first pass with a PINN to find the solution. You then calculate this sort of better loss function, stick that into your deep network, find some more collocation points, and go round. And if you do that, you get a significantly improved speed up in the training of your PINN. So again, that's using approximation theory and deep learning all together. And here's another example. This is a simple linear second order differential equation. On the left, it's trained without rezoning, so it comes down, faffs around for a bit, and eventually finds a solution. But with rezoning, it goes straight into the solution very, very quickly. So it significantly speeds up the whole operation, and in fact, you even get a better answer. That's the good news. Again, this is a conference on dynamical systems. So I'd just like to say one of the dynamical systems I'm really interested in is convection. The very first talk of this conference by Edward Ott was about deep learning and environmental problems, and convection is a big thing that we're trying to understand. So we can ask ourselves, are PINNs any good at solving convection problems? And here's a convection problem. So this is a classic sort of one-dimensional problem you might get as an approximation of Berger's equation or something like that with convection in. And the basic problem with this is they do very badly. And we're not quite sure at the moment why they do badly. They basically, they get into a local minimum and stay there forever. And we've tried, you can nudge it out a bit using homotopy methods, but even then you find they're very hard to train. So there's a bit of a hole there in our understanding of how these things work on the sort of dynamical systems which people might be interested in if they're interested in problems in fluid mechanics and stuff. So that's the bad news, but I want to kind of talk a little bit about some good news in about 5 or so minutes. I've got, how many long? 5 minutes, which is some success that we've had in using PINNs in the context of solving two-dimensional problems, two-dimensional elliptic problems. So here's a kind of classic two-dimensional elliptic problem. We have, say, Laplace U is F, so it's Poisson problem in a domain where you've got some Dirichlet and some Neumann boundary conditions. So this is a problem in finite element land you would always formulate in a weak way. So let's see how we might do that. There's a couple of ways that you can do this in a weak way. One's called the deep Galerkin method, where your loss function here is like this. You try to minimize an energy, which is your residual here, plus something on the boundary. That's the deep Galerkin method. Alternatively, and rather better, I think, is the deep Ritz method, introduced by Wan and E and collaborators, where you you formulate essentially the weak form of the equation, which is this thing here, again, plus the boundary conditions, and that becomes the thing that you're trying to solve. So the deep Ritz method in Wayne and Ian's papers and so on, they applied it to simple convex domains and everything sort of worked all right. So we thought we'd try it on a more challenging problem, or just to say use standard network architecture and all that nonsense, which is to solve this problem on a problem with a corner here. Anyone's familiar with PDEs will know that at the corner you have a singularity. The singularity is x to the 2/3 if x is the distance from the corner, which is why I was interested in x to the 2/3 earlier on in the talk. So that's the Poisson problem on an L-shaped domain. And as I say, you get this, there's your singularity r to the 2/3 as you go into the corner. We know already that it's really hard to approximate that if you're not careful. Okay, so what happens is this is what the solution looks like. And we're going to compare that solution with our underlying solution of the PINN. The PINN is continuous everywhere, but we're still going to have a look at the difference on a Delaunay mesh to get some error estimates. And that is the error on the left of a DGM method, discrete Galerkin. On the right is deep Ritz. And here we're using randomly chosen quadrature points. So this is what you're recommended to do. Choose your points randomly, so you sort of look at this function in an appropriate way, and the answer is rubbish. Okay, really bad if you do this. So nothing wrong with the deep Ritz method, but everything is wrong here with our choice of points. This goes back to our earlier thing about approximation theory. Can we do better? Well, there is a better way to do things. What we had in the approximation theory in one dimension was we had a measure of the interpolation error. If you want to find points in 2D, you take that and augment it with an additional condition, which is to minimize the Wasserstein distance between the points that you have and uniform points. So it's like having a uniform mesh in a different norm. And you can do that using the Sinkhorn algorithm. If you do that, I'm sorry, it's a bit small, but these are the collocation points or quadrature points that you come up with, which nicely cluster in on the corner and are fairly regular elsewhere. And if you do that, there's your solution. That's using deep Ritz and deep Galerkin instead of using the random points, using these points, and it's a way better. So the L2 error, if you use random points, is 0.468, and with these ones, the error is far smaller. So it really does make a difference to choose the right points, and I say these are chosen using optimal transport, and optimal transport nicely leads into deep learning in different ways as well. Okay, and I've got various graphs which show that that's the case if you're interested, comparing the different methods. So that's the good news. Deep Ritz, trained with optimal transport, done using everything else, gives you an answer which looks fine. As I said, this talk is all about where numerical analysis hits deep learning, and that's this graph here. So the blue is numerical analysis, is deep learning, and the red is classic, and this is a discontinuous Galerkin method on the same problem. plotted with the error plotted as a function of number of degrees of freedom. And I hope this picture is right because it tells us a lot. What the picture tells us is that the classic finite element method does what the classic finite element ought to do, which is converge as the number of degrees of freedom increase. The deep Ritz method, on the other hand, doesn't converge. It converges very slowly, and we don't fully understand why. But the good news is that the deep Ritz method, the deep learning method, performs far better, well, better than the finite element method for a low number of degrees of freedom, which is actually good news. So what this is basically saying is if you want a quick solution to our problem, use deep Ritz. If you really want to get an accurate one, use the tools of numerical analysis. And so this picture, in a way, summarizes where I think we are at the moment. But obviously, hopefully, we want to get this blue curve to go much further, quicker down. And that's where the research is going. So just to conclude, PINNs work best when combined with good numerical analysis methods. And this other one here, deep Ritz outperforms discrete discontinuous Galerkin for small d, but not for large. And there's lots and lots more to do. So thank you very much.